Good. Hello, everyone. So we've now clarified last time what these p-values in the SPM table are and related all of that to our theory of random fields previously. But what we left out, as I also discussed last time, was that some of these p-values are actually labeled. I think that's how it says it in the SPM table. It says PFWE core. And this is typically read as family-wise error rate corrected, family-wise error corrected. I think it's without the R, so it's FWE, but it's the family-wise error rate that is of interest. And as we discussed last time, sorry, the p-values make sense even without this interpretation of family-wise error rate control, so we can say what they are, but of course they get these labels for some reason, and yeah, that reason, this is then the next topic we want to discuss. So the topic of this session and maybe the next session is family-wise error rate control. And this relates to the statistical theory of hypothesis testing, as opposed to, for example, parameter estimation. And yeah, to make sense of this term, family-wise error rate control, and also how this maximum statistic that we are looking at relates to that, we need to go through some basic terminology. And for the moment, I structured things as follows. So we first, before we go into the question of multiple testing, where of course family-wise error rate control plays a role, we first remind ourselves of single test problems and what I then term the single test error rate, which is of course the one case scenario analog to the family-wise error rate. So that would be the first thing. Then we talk about test theory and statistical mathematical statistics is fairly general. So because we have something very specific in mind, namely T, F, and Z tests, so mainly T and F tests, but also for historical reasons Z test, we should talk about some more specific kinds of tests, which I call, in analogy with Diekhuis 2014, generalized Neyman-Pearson type tests. And the aim of that is actually just to have one kind of language, one kind of nomenclature for Z, T, and F tests. Yeah, so in principle, one could always, one could also talk about Z, T, and F tests all the time, but one can then also just talk about a generalized Neyman-Pearson type test, which is the generalization of Z, T, and F, and possibly other tests. But yeah, then one has one thing one can refer to instead of three. Then once we are clear about this and also the relation of these two p-values, then we talk about multiple testing, the multiple test problem, which of course motivated the whole random field theory-based approach to p-value correction, multiple testing problems. And then this in relation to the family-wise error rate and family-wise error rate control, so that we know what that means. And then finally, to relate this fairly closely to what we've now seen in terms of the SPM table and all these random variables that were discussed, we discuss what I call maximum based simultaneous test procedures. And see how these relate to the family-wise error rate. So in principle, I thought there would be some master students, except one, and it would be a good start before going into test theory at a fairly abstract level to first go again over the logic of conducting t-tests so that we already have an example in place, which we then always can have in the back of our heads when we discuss the more abstract test theory. Now that we are only 4 people, do you want to be reminded of how one conducts a t-test and then have this as an example for the rest, or do you prefer go into the abstract bit first? So who wants to see the t-test example? There's only one master student, but then on the other hand, this is kind of a master student course.
I think you can sit there for me. I mean, I know kind of.
Good, yeah, so we do it then. Maybe the students who watch it on YouTube also feel reminded. Where is everyone? Is everyone now crazy because there's an EG exam this week, or what's going on? Good. Then let's do this. I think it doesn't hurt, although it's a little bit boring. Then we have that in the back of our head, and we can always map this we can always map the example to the more general theory that we then see afterwards. Good. Let's do this with MATLAB because we can. Then let's do it the following way. Let's call this this function implements one sample t-test as an example of single test problems and generalized Neumann person type tests in particular. Something like this. That would be me. Although I will ask you, and then you co-author. Good, so let's assume, so we do it in the following way. We do it in the GLM style. So we first formulate a t-test, one sample t-test model, which we then sample. And then we, of course, estimate the parameters, and then we evaluate, then we do the t-test, which in the whole framework I call model evaluation, which of course here is kind of a parameter evaluation thing. And so that these are the 4 things that we do. So in real life, you would of course only start here. So start from the model estimation because the data you have we will have obtained in your experiment, but because we're doing simulation, we can simulate reality. So let's assume we we do a t-test on n10 values. So that's the number of data points. And then we are using, of course, the design matrix formulation of a t-test. So how many columns does the design matrix have in a one sample t-test? Two? In a one sample t-test? So everybody, I think of you, except for us, must memorize the design matrix for 2 and 1 sample t-tests in the winter term.
I think so.
So how does the design matrix for 1 sample t-test look? Like?
N times 2.
Why 2? We're doing a 1 sample t-test.
Okay.
So what is the thing about a 1 sample t-test? What do we compare in a 1 sample t-test?
To 0? Or to some value?
Yeah, to some value. So we have a set of n data points, for example 10 data points, and we evaluate the commonly null hypothesis that the true but unknown expectation parameter of this sample is given by a specific value or less than that, and it's usually 0. Yeah. You all memorized that, but then it's all no, except for Osmos. So that's the number of beta parameters. So how does the design matrix then look like? It's also second level FMI data analysis. And what are these values? Why zeros? Hello, how does the design matrix of a 1 sample t-test look like?
It has ones in it?
And something else, or?
There must have been something else. Yes, there must have been something else.
I'm talking about a 1 sample t-test. How does the design matrix look for a 1 sample t-test?
Just one?
And how many?
As many as there are columns in the matrix.
There's 1 column in the matrix.
As many as data points?
Exactly.
So the idea would be that we multiply the beta values with the ones, right?
Yes.
The 1 beta value with the ones.
It's a design matrix, yes.
Yeah.
So the design matrix of a 1 sample t-test is just a column of ones and as many as there are data points. So then we can, because we are simulating things, we can of course choose our true but unknown beta parameter value. So space here. So let's say we choose this to be 0.5. And so that's the true but unknown value. Which other parameter do we have to specify to be able to sample our 1 sample t-test GLM? Anyone?
Yeah, sigma.
So what is sigma? Variance of what? Yeah, well, it's a variance, but a variance of something. Of what is it, the variance parameter? Maybe more specifically.
The data generating process.
Well, of the normal distribution that is the data generating process. So, of course, it could, if we wouldn't be GLM, it could be a different probability distribution. So. Good. Then maybe like this. I don't know. Then we are almost ready for sampling. So how can I sample the GLM?
Yeah, you would make use a normal distribution, right? With the values that we specified.
What kind of normal distribution?
Multivariate.
Yep. So we can use the multivariate normal random number generator, which takes in the parameters of a multivariate Gaussian distribution, which are yeah, x and beta. Which parameter of the multivariate normal do they create? That's what we did the winter term, all winter term. The expectation parameter, exactly. So x and beta create the expectation parameter, or the mean of this distribution, as people also say. And what's the other parameter? Yeah, the variance, but it's a multivariate Gaussian, so how do we call that? Yeah, it's a covariance matrix. And how does this covariance matrix look like for all of the GLM with independent samples?
It's the identity matrix multiplied with, well, the one that is specified.
Yep. So, yeah, so the expectation parameter and covariance matrix parameter of this Gaussian multivariate Gaussian sampling, something like that. Let's see how that works like this. I think the only problem is that for some reason MATLAB does not return the y as a column vector as it would be sensible, but as a row vector. So we transpose the whole thing so that we get a column vector. So a column of data points. Okay, and then we want to do a t-test. Which kind of quantities go into the formula for the t value?
We need our beta estimate and variance. X transpose X inverse or inverse. Inverse.
Well, although MATLAB doesn't like it, but I like it.
Okay. And X transpose times the Y.
So that's the beta estimate. course, we also want to estimate sigma square. How do we do that? It was actually in the exam, I think, this question, which is like 2 months ago or something. Oh, that's great, but I want to now know it from.
But it's the same is divided.
Any idea? It's all forgotten.
But I know where I can look at.
That's something. Good. So you know.
Isn't it x times beta minus y?
Usually I do it the other way around, but which better?
Or beta x.
Mm-hmm.
Transpose times the same.
Mm-hmm.
Then divide by n minus p.
Yeah. Let's have a look. Now we have something new. Good, and then we want to do our t-test. So what do we need to do a t-test? Data we have, because we have sampled it. So maybe a t-value. Maybe that's something we need to do a t-test. We might also decide on a significance level. So let's say we decide for a significance level of 0.05. And how now do we do a t-test? What do we do? That's kind of psychology, statistics, first semester, maybe second. So,
Or beta x divided by square root of sigma square times xt inverse.
Well, that's essentially it. And that's our t-value. So one can do a little bit more in terms of specifying the beta value that one tests against, but this we said would be 0. So that would be our null hypothesis parameter. And what else? Yeah, we can, just to make it kind of in line with what you do when you do this at the second level in fMRI data analysis, we can define a contrast weight vector. But again, this basically doesn't do much, doesn't anything more than what you said. And then we can compute our observed t-value by basically doing what you said. So we multiply our contrast weight vector with the estimate and subtract from it. Let's do this actually in brackets. Our beta 0, but this is 0, so nothing happens there. And then we divide it, as you said, by square root. Again, we can put in our contrast weight vector, which doesn't do anything. Sigma square hat and multiply this by the inverse of x times x, and multiply this again by the contrast weight vector, like this thing. So that would be the t value. Of course, we can also do this directly in MATLAB if we want, and just to make sure that we are doing fine. This is how you call a t-test in MATLAB. So our t-value and the MATLAB t-value are the same. So either we are both order wrong or we are doing okay. Good. So now we've got a t-value, but we want to do a t-test. So what else do we have to do?
And look at the t-distribution. Mm-hmm. Where the t-value is, and then p-value or c p-value.
Mm-hmm. So how do we do that? So there are basically two options. So we can either look up the critical t-value for rejecting the null hypothesis, or we can look up the p-value and check whether that is smaller than the significance level, as we will also later see. But we have to do something. So how do we get there? Mm-hmm. But does the PDF have? Mm-hmm. So you're after the critical t-value. Yeah, okay. So then let's do that. So let's call that's how it will be called later. C alpha is the critical t-value. So how do we get that? Well, the function is called ICDF, but and we have to call it for t and for our n minus p degrees of freedom. But what do we actually want from this function? Mm-hmm. And how do we get that? So the alpha. And do we then get it? Let's see. Hmm?
On both sides.
Yeah, the thing is, you always need to recall what that actually means. So and then it gets clear. I mean, I do it wrong all the time as well, but I think there's no way around to clarifying what this actually means. So we are talking about the cumulative distribution function, which looks like this. What we are looking for is the upper tail. So we want to test against 0 or smaller. So we want to find the t-value for which there are only 5% left, right? Or our alpha value. Yeah. So we want to look up this t-value here, which we call C alpha. And so what we need to put in is 95, right? So minus alpha. Let's see. That looks more reasonable. Yeah, you said something like 1 minus plus alpha or something, but I must have to say, we have to put 1 minus alpha into the inverse cumulative density function. So one has to be very precise. This is, maybe this also makes it a little bit clear why I'm so after the mathematics of things, because you cannot implement anything if you're not clear about the mathematics. That's why I always so much about math. Not because math is great and it's a lot of fun to do things on paper, but because we want to implement it and actually compute things. Good, so that's the critical t-value. And now what are the options for a t-test? What are the possible outcomes of a t-test? Yeah, and in terms of testing?
Rejection.
And how do we decide that?
Yeah, we have already defined our alpha, right?
Mm-hmm.
And now we have to basically replicate p-value or see if our t is lower or greater than the critical value that we just
Sure. So we don't need to
depending on which of the two strategies.
So we can, and because we now have these, then we can do the following. If t is larger than C alpha, then let's call that phi, because we will call that phi later on. Then we reject the null hypothesis, which we encode as phi being 1, else phi equals 0. And people have their opinions of whether you call this null hypothesis acceptance, non-rejection, or whatever. So generally, I'm thinking always in terms of the Neumann person test theory, where you have also an alternative hypothesis, although we don't make it explicit here, and then it doesn't matter how you call that. Good. Maybe let's also check that. No, we don't actually need this H and V, whether we did it the right way around. Yeah. Good, so this is how one does a one sample t-test, and then the next thing now is to generalize this so that we have a language to discuss tests and also multiple tests, not only always for one sample t-test in which you follow this kind of logic, but also can subsume things like f-tests, z-tests, and everything else under this umbrella. Yeah.
Is also non-parametric tests part of the line?
So what I meant there was actually this power non-parametric framework. What we now talk, when we talk about tests, then yes, the general tests, these are all possible tests that one can think of. The generalized one-sided non-person type tests, no, they are, this is essentially just a generalization of the parametric T, F, and Z tests, which I want because we are using these tests in SPM.
Yeah.
So. But the general language of tests is, of course, also applicable to non-parametric testing. Good. Then, after this reminder, to which we will, of course, also come back and now have a reference, let's talk about single test problems. But before we talk about, we can do that in the context, but we have to introduce the notion of a parametric statistical model. So we developed the whole thing under a parametric statistical model, but you can also apply non-parametric tests to parametric statistical models if you want, but the whole theory here is developed for parametric models. Single test problems. And we need, of course, single test problems so that we have a language to introduce multiple test problems. Because how can you do multiple testing if you don't know what single testing means? So the general background to what we will do is given by a parametric statistical model, which is just this tuple of an outcome space of data observations, a sigma algebra over this outcome space, and a family of parameterized measures. Maybe that's why you ask. Was that the motivation? So non-parametric, I don't know actually how non-parametric people define the model they test against. Essentially, non-parametric means that you have infinitely many parameters. If I were to develop a non-parametric approach, or maybe, I don't know how they do it. Because you can apply non-parametric approaches to parametric models, but it doesn't really matter that much. So the main thing here is that we have a clear nomenclature of what we're dealing with. So we have a sample space. So we have something that from which we can sample data. So we can talk about something, the probability for a given parameter setting of a random variate y to take on a value y is this and that, or better to for the data to fall into a specific subset of our event algebra, or our sigma algebra. What we allow here is the possibility to think about different parameters, so that we allow many parameters which we need because we want to partition the parameter space. So that might not be fully clear the way I put it here, so let's call this our so with the double lines, our outcome or sample space, something like this. And then this is a random variable modeling the data, and this is a value of the random variable that lies in our outcome space. So for the example that we've just seen, of course, the y was this thing that we sampled. The possible outcome space was all n-dimensional vectors. and the random variable was the thing that we realized if we would have run the script multiple times. And then I like to talk about that when we apply this whole thing in an experimental context, that there is this true but unknown parameter value, theta star. Although I'm going a little bit back and forth whether one actually needs this. In the example that we've just seen, we had our beta true but unknown beta star and our sigma square true but unknown making up the true but unknown parameter. Yeah. So the question is, of course, if we apply this logic to the random field based p-value correction business, what is the parametric model that underlies RFP? And we haven't made that explicit thus far. I mean, we have the idea that, of course, we have this random fields which realize essentially the errors. So I will try to give an explicit form of this parametric model at one point. Essentially, it comes down to the GLMs for all the different voxels, and then using the random field theory as or the random fields as models for the spatial error. But yeah, so for the moment, with respect to RFP, yeah, maybe also think about what the how the parametric statistical model for RFP actually looks like. We haven't really made this explicit. Good. Then let's before we then really go into a single test problem, let's have a break and then continue at 9, I guess.